This video lesson is the second in a two-part series covering Bernoulli's principle and Darcy's law. Support for the development of this lesson has been provided by the National Science Foundation through Ohio University's Boat of Knowledge and the Science Classroom program. In the previous video lecture, we discussed the basics of Bernoulli's equation and some applications. This video lecture will apply our knowledge of Bernoulli's equation to Darcy's law, and the lesson will end with an application of Darcy's law, rain gardens. Let's start with Bernoulli's equation. Does anyone remember the three terms that make up the equation? We had pressure head, P over gamma, velocity head, V squared over 2g, and elevation head, H. Of the applications that we mentioned, one was groundwater flow. Let's take a look at the role Bernoulli's equation plays in groundwater flow calculations. Groundwater flow is governed by a concept called Darcy's law, proposed by Henry Darcy. Darcy's law states the relationship that Q equals KIA, where Q is groundwater flow, K is hydraulic conductivity, I is hydraulic gradient, and A is the area. Before we can apply this relationship, we need to know what hydraulic conductivity and hydraulic gradients are. We'll start with hydraulic gradient. Does anyone know what a gradient is? A gradient is a change in the value of a quantity with a change in a given variable. Gradients are usually per unit distance and have a specified direction. Gradients can be related to energy, temperature, pressure, or concentration. The hydraulic gradient describes how much the hydraulic head changes over distance in an aquifer. Since hydraulic head has units of distance, and we know gradients are per unit distance, the hydraulic gradient has units of meter per meter. Of the four gradient types, which do you think hydraulic gradient is classified as? Hydraulic gradient is an energy gradient, and the concept is derived from Bernoulli's equation. Since hydraulic gradient describes the change in hydraulic head, let's begin by defining hydraulic head. Hydraulic head is derived from Bernoulli's equation and is given as the sum of the pressure head and elevation head. Why do you think we only use the pressure and elevation heads without including the velocity head? Think about how groundwater flows. For groundwater flow, the velocity is very low. In fact, it's so low that it's negligible when it's added to the other two terms. Since it has such a minimal and unnoticeable impact on the total head value, it can be disregarded when we calculate total hydraulic head. Let's consider an actual application of determining hydraulic gradient and flow direction. If we have three wells in a triangular pattern, for which we know the total head and distance between the wells, we can determine the hydraulic gradient and flow direction. We start with the well that has the intermediate head value. In this case, well 2 has the intermediate head value. Now we need to find the point between wells 1 and 3 that has the same head value of 26.2 feet like well 2. We can find this point by doing an interpolation between wells 1 and 3. We can set up the interpolation with head values in the numerator and distance values in the denominator. On the right side of the equation, we have the values for wells 1 and 3, which are values that we know. We have the head values of 26.26 feet minus 26.07 feet in the numerator, and the distance of 215 feet between the wells in the denominator. We can set this equal to the left side of the equation, which contains the unknown distance in the denominator. In this case, the distance is being measured from well 1, since we are using the head value for well 1 in the numerator. For this side of the equation, the numerator has head values of 26.26 feet minus 26.2 feet for wells 1 and 2. If we solve for x, we find the distance between well 1 and the point with head 26.2 feet is 68 feet. We can connect the 2 points with the same elevation by drawing a straight line from well 2 to the point with the same head value that lies along the line between wells 1 and 3. This line represents a portion of the contour with elevation 26.2 feet. We can determine the flow direction by drawing a line perpendicular to this contour that goes through the well with the lower elevation. In this case, the line will point down and pass through well 3, since well 3 is at a lower elevation than well 1. Now we can calculate the hydraulic gradient as the difference in the head values for wells 2 and 3 divided by the distance of the perpendicular line between the contour line and well 3. The length of the perpendicular line, which is 130 feet, can be determined using the Pythagorean theorem since we have a right triangle. Then the hydraulic gradient equals the quantity 26.2 minus 26.07 divided by 130, which equals 0.001 foot per foot. Hydraulic conductivity, K, describes how effectively water can pass through an aquifer. Hydraulic conductivity depends on the fluid properties and the aquifer material's ability to allow water to flow. It's typically a very small value and has units of centimeters per second or meters per second. Now that we've developed an understanding of the principles governing water and groundwater flow, we can discuss an application dealing with groundwater flow control. This application was the basis of Andy Long's thesis, wherein he investigated how a biofiltration stormwater best management practice could reduce the negative impacts of stormwater runoff on Goose Run, a creek in Marietta, Ohio. This biofiltration stormwater best management practice is also known as a rain garden. Rain gardens are engineered gardens that are located near urban sites with excessive runoff, particularly from parking lots. These gardens are filled with native plants that aid in the retention and filtration of stormwater runoff. What do you think some of the benefits of rain gardens might be? Rain gardens can reduce pollution from stormwater by filtering the water before it enters the stream. They can also reduce urban flooding by retaining the water instead of contributing to runoff. Rain gardens can also help to recharge groundwater supplies, since some of the water that enters the rain garden infiltrates into the ground and returns to the groundwater flow. The combination of retention and reduced runoff amounts means that erosion of streams and creeks will also be reduced. Finally, rain gardens are eco-friendly and aesthetically pleasing. The native plants create an ideal habitat for birds, butterflies, and other native species. The rain garden that was designed and studied in connection with Andy's thesis was located on the Marietta College campus in Marietta, Ohio, near Goose Run. The rain garden was placed next to a 0.7-acre parking lot on the college campus and served two purposes: to reduce the pollutants flowing from the parking lot into Goose Run, and to control peak flow times and volumes to reduce flooding impacts. We can see the general location of this project from the maps shown. Washington County is highlighted in white on the Ohio State map, and the Goose Creek watershed, which is magnified in the lower right picture, is shown in green on the Washington County map. This drawing shows the location of the rain garden with respect to the parking lot and stream. The garden was designed using water quality volume and an application of Darcy's law. The surface area of the rain garden was calculated according to this equation, which incorporates water quality volume, planting soil depth, coefficient of permeability of the planting media, average height of water above planting soil and mulch, and filter bed design time. Calculations were completed using the previous equation. And the final garden design was determined. Monitoring the garden was a challenging and expensive undertaking that required designing a system to capture runoff from the parking lot, measuring the flow in and out of the garden with a flow meter, and collecting influent and effluent samples to test pollutant removal efficiency. Some of the challenges associated with testing pollutant removal efficiency included selecting pollutants to test for, which required a literature review to determine typical pollutants for parking lot runoff. More information about this project is contained in the final thesis report, which includes additional tasks, such as design of the monitoring system, plant biology, survey of Goose Run, GIS and HEC-RAS information. Some basic information about the project is included in the news article provided at the following website. For more practice with Bernoulli's equation and Darcy's law, you can complete the following additional activities that are included as part of this lesson.